Have you ever stared at a 1.7 problem and thought, there's way too many graphs, charts, and arrows to keep track of? You're not wrong. There totally is. But that's not the actual problem. The problem is that nobody showed you the two interactions that explain everything. At the heart of this topic, there's only two interactions. In this video, I'm going to show you exactly what those two interactions are and how to use them to unlock everything in 1.7. Once you see how these two interactions connect, you'll start spotting them in topics you haven't even studied yet. All I need is a periodic table and a little bit of Coulomb. Each periodic trend is going to be handled from one of two directions, either vertically or horizontally. A vertical column on the periodic table is referred to as a group, and a horizontal row is called a period. There are a few exceptions to these rules, but on the AP exam, you're just going to be looking for the general overall trends. That's why the last two rows on the periodic table have been left off the screen here, because that F group on the bottom really kind of breaks a lot of rules. Those behave strangely, so I'm not going to worry about those at all. The main trend that you need to understand functionally at the atomic level in 1.7 is the atomic radius. Everything else connects to this one trend. The atomic radius is measured as the center of the nucleus to the outside of the electron cloud. The atomic radius is based on the interaction between the protons and the electrons. Those are the two you need to focus on. Since the protons are fixed in the center of the atom and the electron cloud floats around the outside, all you need to realize is that the protons are pulling the electrons inward. Just remember, protons suck. How much do they suck? Well, that's based on Coulomb. This was introduced in topic 1.5. If you haven't seen my video on that one, I've got a great introduction to it, but basically Coulomb is based on charge and distance. The charge in question is the nuclear charge, and the higher the nuclear charge, the more protons there are, the more attraction force you'll get from the nucleus. Thus, the smaller the atom. Electrons at the same time repel each other, so as they're swirling around the nucleus, they're going to be pushing outward. The more electrons you have, and especially the more orbitals there are occupied, the larger the atomic radius is going to be. That's it. Protons suck and electrons push out. Let's apply this individually to the vertical axis first, and just take one group on the periodic table. You're not going to have to jump all over the place. If you're dealing with the vertical trend, it will be just one group. For instance, group 1 deals with hydrogen, lithium, sodium, and moving down. But what changes here are two aspects. First, yes, the nuclear charge is increasing as we move down a group. That makes every single orbital just a little bit smaller. However, in this case, adding the additional orbitals as we go down the periodic table is going to cause a larger increase in atomic radius than the nuclear charge will shrink it. So the most impact you get is from the number of occupied energy levels. Down any group, the more energy levels you have, the larger the atomic radius will be. The horizontal trend is a little bit more complicated, and this is the one that most students get wrong. You're dealing with same period elements, so I'm going to work my way across period 2 from lithium all the way over to neon. Now, regardless of which element you're talking about here, all of them have two occupied energy levels. Lithium only has 1 electron, while neon has 8 in that shell, but even though the electrons push out, notice I'm not putting on additional energy levels. So those additional electrons all going into the same energy level, they don't make that significantly larger. And that's the misconception here. What really does make this radius change is the nuclear charge. Those protons suck everything inward, and going from 3 to 10 protons in the nucleus is going to have a much larger impact on that atomic radius. Neon is going to be smaller than lithium. As you move to the right side on the periodic table, you have the same number of occupied energy levels, but a higher nuclear charge, no matter which period you move across. Therefore, the atomic radius decreases as you move from left to right on the periodic table. This is very important and the basis for everything in 1.7, so let me do a quick recap. Repetition builds memory. As you go down any group on the periodic table, you have additional occupied energy levels. That's going to make things get larger. As you go from left to right, the valence shell isn't changing. However, you have an increased Coulombic attraction due to the higher nuclear charge. And the atomic radius is going to get smaller as you move from left to right on the periodic table. The concept of atomic radius is going to be applied within larger problems significantly throughout the AP exam. Make sure you understand how to evaluate these, especially the interactions between the protons pulling things in and the electrons pushing things outward. There's always some questions in the free response specific to topic 1.7, and every one of those covers ionic radius, the radius of an ion. The same interactions are involved, so I want to make sure that I'm always evaluating the electron configuration and the nuclear charge of each substance involved. Likely only one of those will differ. The exam is not designed to trick you, but to check and see if you understand these two interactions. Here's a variation of one of the past FRQs that have been on the AP exam, and it's covering the same two interactions. So let's make sure we cover electron configuration and nuclear charge. You're asked to evaluate the difference in radius for an oxygen ion versus a neutral atom. So the anion is gaining electrons when it forms. Therefore, the O2- has more electrons. In terms of the nuclear charge, they're both oxygen, so they have the same number of protons within the nucleus. The same suck, but the ion's got more electrons pulling things outward. Therefore, the ion is bigger. Notice that my answer covers both interactions. I'm not only saying that it has a larger radius, but because of the same nuclear charge and the different number of electrons. When you have a question that asks an either or like this, in this case, which one is larger, along with a justification, in order to earn the point, you need to make sure that both your choice and your justification are correct. If either one of those is incorrect, you lose the point. Make sure you can explain this in terms of both the nuclear charge and the electron cloud. Next, let's evaluate a neutral atom that becomes a cation. This question actually gives you the size. The radius of sodium is larger than the ion, but it's asking you to explain why. Sodium has 3 occupied energy levels when it's neutral. However, cations empty out their valence shell when they form ions. Therefore, the ion only has 2. That's fewer than the neutral atom. Both of these are sodium atoms, so they are going to have the same number of protons in the nucleus. The best way to frame your answer is based on how the question is asked. This is asking why the neutral atom is larger than the ion. Sodium is larger because it has the same nuclear charge but more occupied energy levels. Notice again that I referenced the nuclear charge and the electrons. These questions are also comparing a common trend, a neutral atom versus an ion. In each case, you're comparing the same element, so you're going to have the same number of protons in the nucleus. The difference is whether it's gaining or losing electrons. Cations form by emptying out their valence shell. That's going to make cations smaller than their neutral counterparts. Anions, on the other hand, are going to get larger because they're gaining electrons when they form. The anion will always be larger than the neutral atom. Now that I've covered 2 questions comparing neutral atoms versus their common ions, let's cover 2 different ions and compare their ionic radius. This one compares a potassium ion and a calcium ion. We need to take into account the same considerations: electron configuration and nuclear charge. Create systems for solving problems. Use these systems in your practice every time you go through, and then you'll be prepared to handle any surprises they throw at you on the AP exam. I can't promise you that these will be the only questions you'll see on the AP exam. In fact, I can guarantee you're going to be surprised by certain things on the AP exam. Calcium and potassium are here on the periodic table. Since these are group 1 and 2 metals, they're going to empty out their valence shell and become cations. When they do this, they're going to have the same electron configuration as argon, so their electron configuration will be the same. However, the atomic number for calcium is higher, 20 versus 19, for the calcium than it is for the potassium. Calcium is smaller because of both aspects. They have the same electron configuration, but calcium has the higher nuclear charge. In the past few years, one of these 2 questions has shown up on the free response just about every single year, comparing the different radii. One of them compares neutral versus the ion, as in the first 2 examples that we covered, the other 2 different ions. Neutral versus ion, you're comparing the same elements, so you're going to have the same nuclear charge, but a different electron configuration. When comparing the 2 ions, these are going to have most likely the same electron configuration, but they're going to have a different nuclear charge. One thing is the same, and the other is different. All of this is based on those same 2 interactions, so make sure you pay attention to the electron configuration and the nuclear charge. don't go anywhere just yet. There's 3 additional concepts that are covered in topic 1.7, but each of these relate to the atomic radius. I do recommend memorizing what each one of these 3 things is, but then understanding them and how they're going to function at the atomic level. You still only need to worry about the nuclear charge and the electron configuration, but mostly how these connect to the atomic radius. I covered ionization energy in my 1.6 video. If you haven't seen that one, I highly recommend it. It's defined as the energy required to remove an electron from an atom. So let me compare 2 different atoms together. I like to think of this as how hard would I have to pull in order to rip one of the electrons off of these? And that has to do with Coulomb, which was covered in 1.5, another great video. And remember, when dealing with Coulomb, the distance matters significantly more than charge. The smaller one has a shorter distance between the nucleus and those electrons. Thus, the smaller the radius, the higher the ionization energy, because those electrons on the smaller atom are going to be held in more tightly by the nucleus. We could also state this as saying that the ionization energy is inversely proportional to the atomic radius. That 1 over the squiggly thing is the symbol for inversely proportional. The electron affinity is the probability that an outside electron will be attracted to an atom. This is a probability, not an energy consideration like ionization energy. However, it's still based upon the attraction from the nucleus. Consider the 2 atoms, this time with outside electrons. Which one's more likely to draw it in? Whichever one has a stronger attraction. And distance matters. So the smaller one has a shorter distance between the nucleus and those outside electrons, therefore it's more likely to pull it in. A smaller atom is going to have a higher electron affinity. Just like ionization energy, electron affinity is inversely proportional to the atomic radius. Electronegativity, in my opinion, is really more of a Unit 2 topic. You're going to use it heavily there, but it is connected to all of these other trends, so it's introduced here. It has to do with bonding, and it's defined as the force of attraction on shared electrons. So let's stick those atoms together. And what we're talking about are electrons that form the bond shared between them. Which one is going to have a greater pull on those? Once again, it's the distance between the nucleus and the electrons that matter. Smaller one is closer, therefore the smaller one has a higher electronegativity. Electronegativity is inversely proportional to the atomic radius. All 3 of these are measuring different things, but they're all inversely proportional to the atomic radius. If you understand the concept of atomic radius and you can compare 2 elements or ions on the periodic table, and you remember the definitions for these, you can figure out which one has a higher or lower value based on any of these numbers. I highly recommend grabbing a second notebook or creating a new file on your computer for something I call a Memorize Me list. Take these definitions and put them on that Memorize Me list. Before you finish Unit 1, go through and create that list for all the things you need to memorize. I highly recommend understanding these concepts, so write them in your own words. You won't be asked to define them on the test, but you will have to describe how the atomic radius impacts each one. So you have to be able to keep them straight in your head. To that end, I thought I'd share some pictures with you that are kind of the thoughts that run through my head as I think of each of these 3 topics. Ionization energy is how hard you need to pull to remove an electron from an atom. And again, that's based on the attraction from the nucleus. Electron affinity is the probability that an outside electron will be sucked in. Well, that's also based on the attraction from the nucleus. And electronegativity is how hard 2 atoms are playing tug-of-war on those bonded or shared electrons. Again, we'll get way more into that in Unit 2. Use whatever tricks you can to help these things stick in your head as you go through the year. And if you ever have any ideas that I can use or pictures that I can put together for you, please feel free to leave a comment below. So here's what I want you to take away from this. Comparing atomic radii will be applied on the AP exam, most likely to ions. Electrons tend to make things bigger, while protons tend to make the atom smaller. Know the 3 terms: ionization energy, electron affinity, and electronegativity. They are all inversely proportional to the atomic radius. I'd recommend creating a Memorize Me file for Unit 1 now that we're approaching the end and start jotting these things down. Trust me, in the spring, you will thank yourself very much for doing this work progressively as you go throughout the rest of the year and not leaving it all for the limited amount of time you're going to have to review for the AP exam. If you found this video helpful, please hit subscribe. I'm trying to motivate myself to put together the 100 plus videos I will need to cover every single topic in AP Chemistry. And knowing that I'm helping and supporting you is the motivation I need. So your comments, your subscriptions, your support, all of those things are going to keep me working so that I can give you the best possible content I can this year. And remember, don't just memorize it, understand it. Thank you again. See you in the next one.